Okay, we have been solving systems using elimination, and we've been only looking at the really simple equations where we had either both x's had the same coefficient or both the y's had the same coefficient. So it was easy to eliminate one of the variables. What we're going to look at now are examples where the variables are not the same. So problems that look like this one. We have negative 2x plus 15y equals negative 32. And we have 7x minus 5y equals 17. X's are not the same, y's are not the same. So what we're going to do is actually manipulate one of these two equations. There are examples, and we'll get to that in just a minute, where you would manipulate both equations. But for this one, we're just going to manipulate one of them. And by manipulating, what I mean is we're going to multiply one of these equations by a specific number to make it match the other equation. So we're basically forcing like coefficients using multiplication. Now, you know, you've been told this multiple times, that you can do anything you want to an equation as long as what you do to one side of the equation, so whatever I decide to do to one side, I have to go to the other side of the equal sign and do the same thing. So with multiplication, if I decide to multiply this side by a specific number, everything over here will be multiplied by that number, and so will everything on this side. So we need to decide what number we're going to multiply by. How do we figure that out? Well, basically what you're trying to do is you're trying to make one of the variables, x or y, look the same in both equations. So look at negative 2. Can I multiply negative 2 by a number to make it look like 7? And several of you all probably thinking, no, you can't do that. And some people may think, well, actually, there is a decimal that I can multiply negative 2 by to make it 7. And you are correct. But we're going to stick with just integers. We don't want to deal with decimals and fractions. So only negatives and positives with our integers. So is there an integer number that you can multiply negative 2 by to get 7? And there's not. Think in reverse. Is there an integer that I can multiply 7 by to make it negative 2? And again, that number doesn't exist. So we cannot force the x's to be the same. So let's go to our y values. And let's think the same thing. Can I make 15 look like 5 by multiplying by an integer? Or can I make 5 look like 15? So hopefully your brain's kind of churning and it kind of comes to you quickly. Oh, you should be able to multiply by 3. If I take 5 and multiply by 3, I'm going to get 15. Now, we just discussed this. I can't just multiply this by 3. I have to multiply the entire equation from left to right by 3. Everything on the left-hand side and what's on the right-hand side must be multiplied by 3. I can't just pick and choose different values. So here's kind of the what you know and that sort of thing. You know you can't solve this quickly using graphing or substitution. This is kind of a plan of action if you think through this whenever you come across systems of equations. Graphing, if it's in y equals mx plus b form, that's your slope-intercept form, going to be easy to graph. Substitution, if you have one of the two equations solved for a specific variable, the variable's by itself, substitution will probably be pretty easy. In this case, we're going to use elimination, but it's still not going to be able to be done quickly as far as we can't immediately jump into elimination. What we've got to do in our plan here is multiply one or both, in this case just one, of the equations by a constant so that our coefficients are the same or opposites. Ours are going to be opposites because one's positive and one's negative, but the number itself here will be the same. So this is what we just discussed. We're going to take that second equation, 7x minus 5y equals 17, and multiply it by 3. So they rewrote the problem, which is pretty good practice if you rewrite it so that you can see it there in front of you and you can manipulate it. The first equation has not changed. It's still negative 2x plus 15y equals negative 32. We're not doing anything to the first equation. But the second equation, this is the one we're going to multiply by 3. So let's double check all of this. 7x times 3 gives me 21x. That works. Negative 5y times 3 is negative 15y, so that's correct. And then on the other side of the equal sign, 17 times 3 does give me 51. So the multiplication there is correct. So now that we have multiplied that equation by 3, you can see that our y values will be eliminated. Now you have to determine add or subtract. In this case, we are adding the equations. A positive 15 plus a negative 15 is going to give you 0. So we're able to eliminate those y's. If you add negative 2x and 21x, you do get 19x. And negative 31 plus 51 gives you 19. So if you solve that for x, just divide by 19, you get 1. Now, just like with the other problems, we know our x. Now we have to solve for our eliminated variable, which in this case is our y. Now, one good rule of thumb is to use either of the original equations. Just in case you have an error in your multiplication, but you happen to get the answer right here, you always want to go back to the original two equations when you use substitution. So, they picked the second equation. In place of x, they're going to put 1. So they rewrote the problem by putting a 1 in there for x. And then just solve that. 7 times 1 is 7. It's a positive 7. So you'll have to subtract 7 from both sides. And then don't forget this negative with the 5. So this is negative 5y. So you'll have to divide both sides by negative 5, which leaves us with negative 2. So our x is 1, our y is negative 2, and so this is our solution, 1, negative 2. Now over here it asks you what could you do, how could you show that this is an original solution? First of all, this is a typo here. The negative's in the wrong spot. This should be a positive 1 and a negative 2. That's our solution here. But what you can do is take your solution and plug it into the two original equations. Make sure that it works in both, and then you would know that it is the correct solution. All right. So now it's your turn. Here's your system of equations. You're going to use the multiplication property of equality. That property, remember, is where you multiply one side by the same number that you do the other side. Basically, what you're trying to do is you're trying to make one equation look the exact same as the other equation. Okay, so decide which variable you can actually make look like the other one, and then solve it. Now, these are your answer choices. This is what you're going to do. Multiply the first equation by 2, multiply the first equation by 3, multiply the second equation by 5, or multiply the second equation by 6. This is what are you going to do? How would you solve this? Okay, so think about that. Look at your two equations. Think about that. And the correct answer is actually going to be B. You're going to multiply the first equation by 3. And if you multiply the first equation by 3, then your two equations, your y values are actually going to be the ones that match. Now, when our solution page pops up here, this is just an explanation of multiply the first equation by 3 to eliminate the y's in your system. So what I would like for you to go ahead and do is multiply this by 3 and go ahead and solve the system equations. And if you have any questions, make sure you ask when you come to class. Now we're going to look at an example where the two equations, you cannot multiply just one equation. You're going to actually have to manipulate both.
In this problem, you will solve a system by multiplying both equations. What is the solution of the system? Use elimination. The first equation in the system is 3 times x plus 2 times y equals 1. The second equation is 4 times x plus 3 times y equals negative 2. Step 1. Multiply each equation so you can eliminate one variable. How can you get started? Find the least common multiple of the coefficients of the variable that you want to eliminate. Multiply to make the coefficients equal to the least common multiple. For this problem, multiply to make each coefficient of y equal to 6. First, multiply the first equation by 3. Now multiply the second equation by 2. Now that the coefficients of y are the same, you can subtract the equations to eliminate y. So x equals 7. Step 2. Solve for the eliminated variable. Use either of the original equations. You can use the first equation. Substitute 7 for x. Then simplify. Subtract 21 from each side. And divide each side by 2 to solve for y. So y equals negative 10. The solution is the ordered pair 7, negative 10. Now it's your turn.
Okay, go back and look at that example if you need to, but how are you going to use the property that we just talked about, the multiplication property, to change these equations? Okay, basically, what are you going to multiply the first equation, and what number are you going to use to multiply the second equation by so that they can match? Now, here are some answer choices. You're either going to multiply both equations by 2, so think about that. Would that make x's and y's both match? Or the x's match or the y's match? Multiply both equations by 3, and so forth. You can read those. So decide, what am I going to do to actually begin making these look the same? Either my x's are going to be the same or my y's will be the same. Now, hopefully you've thought through that, or maybe you've paused the video. The correct answer is going to be D. You're actually going to multiply this first equation by 2 and the second equation by 3. So what I would like for you to do is I would like for you to go through and multiply the first equation by 2 and also multiply the second equation by 3, and then look at your two new equations and go ahead and eliminate the variable that has the common or the same coefficient. Once you've multiplied your two equations, you're actually back to the very first type of elimination questions we did, where they matched and you could simply eliminate immediately.